Alright, it's NIAKQ. So today we are going to have a NIAKQ chemistry series. So we are starting with the topic number 1, which is the states of matter. So we are going to dissect each and every objective within the syllabi so that you can have the better understanding of fundamental principles. So always remember to subscribe, to follow, and to like. So on TikTok it's NIAKQ Osteozone, and on YouTube it's NIAKQ O level for the O levels, and then NIAKQ A level for the A levels. We are providing a massive revisions, tutorials in all the science subjects. We have a lot of tutors who specializes in different specialties. So if you happen to have any question which you feel like it needs our attention, don't hesitate to message the admin so that we can discuss the questions over here for the benefit of others, right? So we are starting with this first topic, so states of matter. So first you need to understand what is meant by this term matter, right? So matter is defined as anything that is mass and volume. Anything that is mass and volume. So we can say that it is defined as anything that is mass and volume. So this is the simplest definition of matter. So we need also to define the term mass, right? So mass is defined as the amount of matter within a substance, right? So this is the definition for mass. And then we go on to define or to give the states of matter. So we say that matter is defined as anything that is mass and volume, anything that occupies space and has mass, space which is the volume, right? So we have examples of matter. We are having water, we are having all the molecules, oxygen, carbon dioxide, iodine, and then sodium, and then etc., right? So you should know these are the chemical formulas, right? You should know the chemical formulas. You should familiarize yourself with these chemical formulas. So we are going to say we say that matter is anything that is mass and volume. So matter exists in three phases. We have 3 states of matter. So let us say this is our matter here, and it is divided into 3. We are having 3 states of matter. So here we are having solids, and then here we are having liquids, and then lastly here we are having gases, right? So you should understand the properties of each of these states, right? So we are starting with solids. So in solids, the particles are closer to each other. They are closely packed together, right? Meaning to say this is our solid, where the particles are closely packed. The particles are closely packed together, right? So this one, please don't mind my drawings. Just appreciate how the particles are arranged in the solid phase, right? So this is the arrangement of particles within the solid. So in the solid phase, the particles are closely packed together, right? So we say the particles. So the particles are closely packed together. So this is the first appreciation on the solid phase, right? And then there are little spaces between the particles, right? We have little space between particles, right? And we also know that the particles within the solid phase, they move by vibration. Contrary to other publications, we say they doesn't move. They move, but they move by vibration. Vibration defined as a movement in a fixed position, right? So the particles, they move by vibration, and then vibration is defined as the movement in a fixed position. So let us define vibration. So a time to be examined to define the term vibration. So vibration is the movement in a fixed position. Are we together? And then the other properties of the solid phase are they have lead to energy, they have lead to kinetic energy, the moving energy, right? So they have lead to kinetic energy, right? So they have lead to kinetic energy. And then also the solid, they have a definite shape. They have a definite shape, and then a definite volume. So these are the properties of the particles within the solid phase. And also you should know that the forces of attraction, the electrostatics forces of attraction between the particles are the one which yields the definite shape, right? The one which yields the definite shape. Are we together? So we are going to explain this liquid phase. So let us explain the liquid phase here. So we are done with the solid phase. So this is what you need to know for the solid phase. The particles are closely packed together. They move by vibration. Vibration defined as a movement in a fixed position. They have lead to kinetic energy, a definite shape, and then a definite volume, right? And then the volume or the shape is held by the strong electrostatic force of attraction between the particles. Are we together, guys? So we are now moving on to the solid phase, to the liquid phase. So this is the liquid phase. So we go on to the liquids. So the liquids. So let us start by highlighting the structure within the liquid phase. So the particles are relatively apart from each other compared to the solid, right? So this is the arrangement of the particles in the liquid state. So the particles are relatively apart from each other compared to the solids, right? So let us highlight the particles relatively far apart compared to the solids, right? And then they have more kinetic energy compared to the solids, right? So more kinetic energy compared to the solids, right? And then the next part, we can say that they've got a definite volume, and they doesn't have a definite shape. They take the shape of a container. I need also to take note on that one. So they have a definite volume, no definite shape. They take the shape of a container. So these are the properties of the liquid phase, right? The particles in a liquid phase, they are relatively far apart. You can compare the distance, this distance between the particles, and then the distance between the particles in the solid phase. So in the liquid phase, the particles are relatively far apart compared to the solids, and also the particles they have higher kinetic energy compared to the solids, and then they have a definite volume. They take the shape of a container. So this is the simple explanation of the liquid phase. So we are now moving on to the gaseous phase, right? So we are done with the liquid phase, and then done with the solid phase, and now we are moving on to the the gaseous phase. Are we together? So this is the gaseous phase, the gases, right? So first we are going to draw to illustrate the arrangement of the particles, right? So the particles in the gas, they are far away from each other. So whenever in your exam you're given a diagram and you see the particles far apart from each other, you can tell this one is the solid, this one is the liquid phase, by simply understanding the given diagram, right? So we want to highlight or to give the properties of the gaseous phase. So the particles in the gaseous phase, they have the most kinetic energy, right? So kinetic energy increases from solids going on to liquid and then finally gases. So my gases, they have the highest kinetic energy, and then the solids, they have the lowest kinetic energy, right? So you should take note on that one. And then the strength of the intermolecular forces, the strength of the forces holding the structure, what you call the lattice structure. So we have what you call the lattice structure. So basically this arrangement of particles, this arrangement is what you call the lattice structure, basically, right? So we're going to explain much on the lattice structures as we dive into the molecular structures, the giant molecular structures, the symbol, and etc. So we're going to discuss much on that one, but you need to have the general appreciation of these lattice structures, right? So the strength of the lattice structure decreases as we go down this trend, right? So the solids, they have the highest strength of intermolecular forces compared to the liquids, and then the gases, they have the weakest intermolecular forces, right? So intermolecular forces are what governs boiling point and melting point, right? Simply saying the solids, they have a higher boiling point compared to the gases in general. So when you are given a gas and a solid, and you are asked to give or to comment on their boiling points, basically a solid, you have a higher boiling point and a higher melting point compared to the two. Why? Because of the strength of the forces, right? What you call the electrostatic forces of attraction. So this is what you need to know. And we go on to say the particles are far apart from each other, far away or apart from each other, and then no definite shape and volume, and also they take the shape of the container, they take the shape and the volume of the container. Are we together, guys? So this is what you need to know for the gases, the solids, and the liquids. You need to appreciate the lattice structure, the arrangement of the particles, and just try to comment what you are seeing on the diagram. The particles far apart from each other, and try to explain why the boiling points changes, the strength of the boiling points, right? So we are moving on to what we call the kinetic theory of matter. Kinetic theory of matter. So kinetic theory of matter, you need to state what you call the kinetic theory of matter. So kinetic theory of matter states that matter is made up of particles which are always in motion, right? So it states that matter is made up of particles which are always in motion. So we said the ability or the what determines the movement of the particles is the strength of the forces within the particles. So let us say we are having two particles here, and then the strength of the forces holding these two particles is stronger. We then conclude that at the rate of movement of this particle is very slow. Why? Because of this strong bond with this one, right? So let us say we are having two gases, one gas here and then one gas here, and then this one is the bond between the particles, or the force of attraction between the particles. So the longer bonds or forces, they are weaker. So we're going to explain why when we are doing A-level chemistry, but for now just appreciate that the longer bonds are weaker. So we're going to discuss much on that when we are doing A-level chemistry. So let us say we're having element atom A and atom B, and then this one is the force between them. So this one is very weak, meaning to say the movement of this particle is very faster. It has a higher kinetic energy. But this one A and this one B, because of this shorter bond which is stronger, A is going to be more attached to B compared to this one, the attachment of this A and this B, right? So the kinetic theory of matter states that kinetic energy is higher in the gases. Kinetic energy is higher in the gases, and then decreases in the liquids, and then lastly in the solids. So in the gases we are having these longer bonds, and then the liquids is a slight reduction in the length, and then in the solids there are stronger forces holding the particles, right? So the kinetic theory of matter states that the kinetic energy decreases from the gaseous phase, the liquid phase, going down to the solid phase, where we are having the lowest kinetic energy. And matter is made up of particles which are always in motion, right? So we said the solids, they move, though they have the least kinetic energy, they move by what we call vibration, right? Vibration defined as a movement in a fixed position. Are we together, guys? So you should take note on these theorems, right? The kinetic theory of matter, because you're going to be examined on that one. And also to understand why the gases have higher kinetic energy compared to all the other states, right? The liquid and the solids, right? You should be able to explain these things. Do not just claim these things, but you must have the understanding. You must understand the difference and to explain why the gases, they have a higher amount of kinetic energy, right? So we are moving on to the next objective, where we are required to explain the changes of states of matter, right? So I'm going to simplify this one. We are having solids, and then we are having liquids, and then we are having gas here, right? And then we are having solid again, and then we are having liquid, and then gas again, right? So I'm going to simplify this one first using this direction. So from solid to liquid, this is what we call melting. And then from liquid to gas, this is what we call evaporation, right? And then we go back in this direction, from gas to liquid, this is what we call condensation, right? And then from liquid to solid, this is what we call freezing or solidification, right? As simple as that. So this is what you need to know for the states of matter. When we are going to have this in a table format, so let me draw this in a table format so that you can understand. So we said we're going to have the initial state, we are going to have the procedure, and then we are going to have the final state, and then lastly we are going to have the method, right? So we are going to have solid, and then solid is the initial state, and then the final state being liquid. So from solid to liquid, which procedure are we using? We are going to have heat being taken in, right? And then the method is called melting. And then we go on to the next one. So the next one, we are having liquid converted into gas. So liquid to gas, which procedure we are heating? And then the name, evaporation or boiling, right? And then we go on to the next one. So the next one, we are having gas, and then the final liquid. So gas to liquid, this is what we call cooling, right? So from gas to liquid, we are having cooling. And then which method? We are having condensation, right? Or liquidification. Are we together, guys? And then we move on from which one? Liquid to solid. Liquid to solid. So we are cooling again. So I'm going to explain the effect of cooling, right? I'm going to explain the effect of cooling. So from liquid to solid, this is what we call freezing or solidification, right? Freezing. And then we have another one from gas to solid. So from gas to solid, cooling again, the procedure. And then the name, from gas to solid. So this is what you call sublimation. Are we together? And then also from solid to gas, we are going to have heating, and this is also called sublimation. So don't worry about these terms, reverse sublimation, de-sublimation. Just know it in this way, sublimation, right? So this is the table. We are having initial, procedure, in final state, and then the method. So you need to know this table by heart, right? You need to know this table by heart. Are we together, guys? So I'm going to explain on the procedures. So we have heat being taken in, and then we are having cooling and heat being taken in. So these are the two procedures we are having here, right? So I'm going to explain this one with respect to the kinetic theory of matter. So we are having so let us take this one as the example, from solid to gas, and we say it is what we call sublimation, right? So we said sublimation, it's not necessary for this stage for us to explain it in terms of desublimation and sublimation, just to know that it's sublimation, right? So we are moving from solid to gas, and then we are having heat being taken in. So we are having this one. So we said the particles within the solid phase, they're closely packed together. So these are the particles in the solid phase. So we want to break the forces between these particles, right? We want to break this bond so that we have the particles which are further apart from each other. So we are going to have heat being absorbed, right? So this one is what we call the endothermic reaction. So we're going to explain much on that when we are doing energetics, chemical energetics, right? So heat is being absorbed, so heat is being taken into the system. So this solid phase, we absorb heat to break this bond so that we are going to have the particles which are far apart from each other, the gaseous phase. But let's say we are having this one from liquid to solid. So from liquid, the particles in the liquid, they are slightly closer to each other, right? So these are the particles within the liquid, and then you want them to be in the solid phase. So the solid phase, the particles are far apart, closely, tightly packed together, right? So these are the particles in the solid. So we want to reduce this bond angle, bond length. We want to reduce this length between the particles. So energy is being removed from the system. So once we remove the energy, the particles are going to move closer to each other. The particles are going to be closer to each other, right? So this is the effect of cooling. So the effect of cooling will reduce the kinetic energy of the particles. The particles will be closer to each other since they are not moving. And then the effect of increment in temperature by heating will cause the particles to have higher kinetic energy, thereby breaking this lattice structure or this solid phase. Thereby the particles are further apart from each other. So this is what you need to know from this table, explaining it using the kinetic theory of matter, that increase in temperature will result in increase in kinetic energy, and then decrease in temperature by cooling will result in decrease in kinetic energy, right? So this is what you need to know for this cooling curve. Are we together? And then we're going to explain another phenomenon. So this is what you need to know for the cooling curves. So we have what we call the cooling curves. So let us move to a fresh page. So this is the curve, right? So don't mind my drawing. So we are having this one, and then this one, and this one. So we are having ice here, the warming up of ice, and then ice melting here, and then we are having water warming up, and then we are having water boiling here, right? So this is what you need to know. So here we are having temperature, right? And then here we are having time on the horizontal axis. So you need to understand why this phase is a horizontal line. Why this phase is a horizontal line. You need to take note on that one, because at times you'll be examined to label the curve, right? The graphs, right? So you need to highlight that this region is when the graph is parallel to the horizontal axis, right? So why? Because we're going to explain much when you're doing what we call the latent heat of fusion and the latent heat of vaporization. Why this temperature is constant, because this one is a constant temperature, and also this one is a constant temperature. We're going to explain much on that one when you are doing latent heat of vaporization and latent heat of fusion, right? So for now, just appreciate that this one is a horizontal line, and then this one is a horizontal line, and then here we are having a uniform increase in temperature, and then here we are having a defined uniform increase in temperature. As simple as that. Are we together, guys? So for now, what you need to know, you also need to give the examples of the reactions from solid to liquid, liquid to gas, this to this, and then this to this, and also for the sublimation. So for sublimation, we're having dry ice to carbon dioxide. Dry ice is solid carbon dioxide, right? So we're having dry ice to carbon dioxide. So dry ice is solid carbon dioxide. We also have soot, which is unbent carbon to carbon itself, right? So these are the examples of particles which undergo sublimation, right? And we are also going to, so this one is the gas, right? And then this one is the solid, and then this one is the solid, and then this one is the gas. So you should take note on that one. Are we together? And then we are now diving into what we call diffusion. We are diving into what we call diffusion. So diffusion is defined as the movement of particles from the region of higher concentration to a region of a lower concentration, right? So diffusion is defined as the movement of particles from the region of their higher concentration to the region of their lower concentration. Down a concentration gradient. So it's repetition, but we want to highlight that one. So down a concentration gradient. So in biology we have these processes. We have diffusion, we have active uptake, and we have osmosis. So osmosis is the movement of water molecules down a concentration gradient through a partially permeable or a semi-permeable membrane. And then active uptake is against a concentration gradient, movement from the lower to the region of higher against a concentration gradient using energy. And also you need to take note that a diffusion, it is a passive process. What do we mean by the term passive process? We are simply saying that it doesn't require the use of energy, right? It doesn't require the use of energy. Are we together? So diffusion, it is the molecular movement of both liquids and gases, which will then result in their normal distribution. So the other features of diffusion, it will result in the normal distribution of the particles. In the normal distribution, normal uniform distribution, should be uniform here, normal uniform distribution of the particles. That's always in the liquids, right? So we have factors which affect diffusion. We have the factors which affects the rate of diffusion, right? So diffusion is generally the movement of particles, but we have the rate. So when we are talking of rate, we are talking of time taken for the diffusion process, right? So the rate of diffusion is governed by factors. So we are having temperature, we are having concentration of the particles, and we also have what we call the molar mass. So these are the three factors which governs the rate of diffusion. Are we together? So these are the three factors which governs the rate of diffusion. So temperature, so we said the increase in temperature results in the increase in kinetic energy, what we call the moving energy, right? So increase in temperature will then result in the increase in the rate of diffusion. So increase in temperature will result in the increase in kinetic energy, which will then result in the increase in motion, molecular motion of the particles, or molecular movement of the particles, right? Motion of them. Are we together? And then this will result in the increase in the rate of diffusion. So this simply means that if you are having lower temperature, it will be the opposite of all of these factors. So a decrease in temperature will result in decrease in the rate of the kinetic energy, decrease in the motion of the particles, which will then result in a decrease in the rate of diffusion, right? And then we go on to the next concept, which is concentration. So concentration, we are saying that the increase, the particles will result in faster diffusion if they are highly concentrated. So the higher the concentration, the higher rate of diffusion. And the opposite is true, right? So you're saying that the lower the concentration, the lower the rate of diffusion. And then lastly, we go to molar mass. So this one is defined by what we call the Graham's law of diffusion. Molar mass, defined by the Graham's law of diffusion. So what does the Graham's law of diffusion say? So I'm going to simplify this one so that you can understand. So the law says the rate of diffusion is inversely proportional to molar mass. The rate of diffusion is inversely proportional to the molar mass. So this simply means if you are having a higher rate, the molar mass is reduced. If you are having a higher mass, the rate is reduced. As simple as that. So this is the Graham's law of diffusion. The lighter the particle, the faster the rate of diffusion. The heavier the particle, the slower the rate of diffusion. So we are saying that lighter particles, they diffuse faster compared to heavier. So heavier particles, they diffuse slower compared to the lighter particles. As simple as that. So this is the Graham's law of diffusion. So we have this frequently examined question with regards to the Graham's law of diffusion. So the question comes like this. You are given this test tube, this tube, right? And then there's a stopper here, and then a stopper here. And we are told that this one is the end A, and then this one is the end B. And then we are having cotton wool here, and then cotton wool here. So the cotton wool at A is soaked in ammonia solution, and then the cotton wool at B is soaked in hydrogen chloride gas or hydrochloric acid. So the question says, where are we going to have the reaction of ammonia and hydrochloric acid? So they want to test whether you are familiar with the effect of mass on the rate of diffusion. So for ammonia, first you need to understand the molecular mass of ammonia. So the molecular mass of ammonia is derived from the molecular formula of ammonia. So ammonia is a molecular compound. So this is the ammonia, and then hydrogen chloride. This one is the hydrogen chloride. So for us to have the molecular mass of ammonia, we are having 1 nitrogen and then 3 hydrogen. So the mass of nitrogen on the periodic table is 14, right? So nitrogen is number 7 on the periodic table, and then we are having 3 hydrogens, so by 3, so we are going to have 17. So here we are having 17, and then hydrogen chloride 1, and then this one 35.5 to give us 36.6. So this one 36.6, 36.5, I mean 36.5. So we said the lighter the particle, the faster the rate of diffusion, and then the heavier, the slower the rate of diffusion. So this means that ammonia is going to diffuse faster compared to hydrogen chloride. Ammonia is going to move a greater distance compared to hydrogen chloride. That's the rate of diffusion, right? So ammonia is going to move till it reach the other half of hydrogen chloride. And then hydrogen chloride is going to move a shorter distance. Why? Because it is heavier. So the rate of diffusion is slower. So we are going to have the reaction at this point. We are going to have the reaction at this point, near the end where we have hydrogen chloride. So this is the point of reaction. So at times in the examination, you are being required to give where the reaction will occur. You are being required to label where we are going to have the reaction. So this is the point where we are going to have the reaction, the point near the end of hydrogen chloride. Are we together, guys? So to explain this, we are going to use the Graham's law of diffusion, which says the rate of diffusion is inversely proportional with the molecular mass. So we use the molecular masses to point where the reaction is going to occur. So this is what you need to know for diffusion. And if you know this by heart, you are good to go for each and every question being examined on the states of matter, diffusion, right? So we are now going to conclude this session, and if you happen to have any question, feel free to message us in the comment section, and always remember to subscribe, to follow, to like, and to share. Thank you.